We are looking at rates of change today. So there's lots of syllabus dot points that this particular exercise covers. I won't go through them, but the main focus is we're going to understand the and interpret the concept of rate of change in mathematical and real world context. So you'll feel successful if you can describe the rate of change as the gradient of a function at a point or over an interval, and you can calculate the average and instantaneous rate of change from equations, tables or graphs, and you can apply rate of change to solve contextual problems such as speed, cost and growth. So the gradient of a straight line measures the constant rate of change of y, the dependent variable, with respect to the change in x, our independent variable. So how we find our gradient of any straight line is we use the formula rise over run. That's where we have if we have a point, so in this case over here we have that this point here is x1, y1, and this point up here is x2, y2. So using those 2 points, we do the difference in our y, which is y2 minus y1 over our x2 minus our x1. Now, when the gradient of a straight line is positive, meaning it's going up from the left to the right, it is increasing. And when the gradient of a straight line is negative, the line is decreasing. So what we are looking at is also what happens with the gradient of a horizontal line. So the gradient of a horizontal line is 0. The gradient of a vertical line is undefined, okay? It's neither 0, positive, or negative. So straight lines increase or decrease at a constant rate, and the gradient is the same everywhere along the line. This graph off to the side is an example of the distance travelled by a car over time. So how we work out the speed or the rate that the car is going is we do our rise over run. And so our rise is our amount going up. So from one point to the next point, our rise is 400. So to get to this point here, we have risen 400 over a run of 5, and 400 divided by 5 is 80. So the line is increasing, so it means it has a positive gradient. It's going up from the left to the right. And what this means is that the car is travelling at a constant rate, so a constant speed of the kilometres per hour popped down the bottom there. So at 80 kilometres per hour. So the gradient of the line represents the speed of the car, the rate of change of distance travelled over time. Now, on the next page, I want you guys to really quickly have a go at, we now have a graph that shows the number of cases of flu reported in a town over several weeks. I want you to work out the rate of the flu. So just note that the number of cases are in the hundreds, so that this 15 is really equal to 1500. Okay. So you should have your gradient is rise over run. Now, is this gradient going to be positive or negative? From the left to the right, we're going down, so it's going to be negative. So it's going to be negative 1500 over 10. So that means our gradient will be negative 150. Okay, so the rise is a drop. So to get from a point to the point going from the left to the right, we are dropping, so that means it's negative. This means that the rate is negative 150 cases per week, which is really good because the number of people that have the flu is going down, which is something that you want. You don't want people to have the flu, right? And so we can say that this is reported as the number of flu cases is decreasing by 150 cases per week. Okay, so we can either use the negative 150 or we can just use that it's decreasing by 150 cases. Now, that is all stuff that we've seen before to do with our gradient. It's just to connect it to what is happening here. Now, what we're going to be looking at is our average rate of change to start off with. We have two different rates of change. We have our average rate of change, and then we also have our instantaneous rate of change. So our average rate of change is just an average that we're getting, whereas our instantaneous rate of change is the exact rate of change. So we have an estimate and we have our exact. Our average rate of change between 2 points on the graph of a function y equals fx is the gradient of the line joining these 2 points, as demonstrated on our graph over here. So we have that the line is going through the points A, which is the coordinate A and f of A, and B, which is the coordinate B, f of B. What we have is that this line that we have drawn going through our 2 points is called a secant. So what we have is that our gradient, using our gradient formula, is y2 minus y1 over x2 minus x1. But we can also write this as in terms of our a f of a, because they're our points, and our b f of b. So we'd write our function at b minus our function at a all over b minus a. So this is just a different way of writing it. Now our average rate of change of y with respect to x can be written using delta notation. So we've seen delta before when we have done our, our discriminant, okay? But delta, our triangle delta, stands for change in or difference in. So if we have delta y over delta x, it is equal to the change in y over the change in x. Now, when we're talking about a fraction like this, we can also say that it's the change in y with respect to the change in x, okay? So when it's down the bottom, we say that it's with respect to. So the average rate of change of y with respect to x for a function y equals fx over a domain of a to b is delta y over delta x equals f of b minus f of a over b minus a, okay, which is the gradient of the secant. Pretty much all you need to remember is that we're using our gradient formula. If you use y2 minus y1 over x2 minus x1, that's perfectly fine. If you would like to use this new notation, you can also do so. So what we have in our example is we have this graph shows the distance d in kilometres that a car travels over time t in hours. After 1 hour, the car has travelled 50 kilometres, and after 3 hours, the car has travelled 200 kilometres. We want to find the average speed of the car. So on our graph, what we're going to do is we're going to put a dot at 150. So that's at 150, and we're going to also put a dot up at 200. And then we're going to draw a line between our two dots because we are going to be finding the gradient of that secant, okay, which is that line. So in order to find the gradient of that secant, what we want to do is we want to use our gradient formula. Now, I'm guessing that most of you would feel most comfortable when finding the gradient to use m equals our y2 minus y1 over x2 minus x1. Okay, and as long as you know to use that, it doesn't matter if you prefer to use the other one. We know that we have the point 150 and we also have the point 200. So that means we'll have our x1 is 1, our x2 is 50, our y1 is 3, our y2 is 200. So our gradient will be 200 minus... Oh, yes. Goodness gracious. Sorry. So it's our x1, y1, our x2, y2. Sorry. Oh, it's like I'm still asleep this morning. So what we have is we've got 200 minus 50 over 3 minus 1. So when we put that into our calculator, we get that our gradient is equal to 75. Now, were we asked to find the gradient? No, we're asked to find the average speed of the car. And this was a worded question. So we want to answer it with some words. So we want to say that therefore the average speed of the car is 75, helps if I do a 5 properly, kilometers per hour. Okay, so we want to explain what we're saying in our question so that we're answering it correctly. Amazing. Okay, our next example, we're given the function f(x) equals x squared. Again, we want to find the average rate of change, but we want to find it between x equals 1 and x equals 1.1. So whenever we see the average rate of change, our average rate of change is telling us to find the gradient of the secant. So whenever you're asked to find the average rate of change, you're asked to find the gradient of the secant. If you're ever asked just to find the rate of change, that means that we'll differentiate, which we'll talk about in the future. So what we have to find the gradient of our secant is our m, I want to change colours, is our m equals our y2 minus our y1 over our x2 minus our x1. Now, from our question, we're told that our x1 is equal to 1. How can we find our y1? We can find our y1 by substituting in our x1 into our function that we've been given. So we can find our y1 by y1 will equal f of 1, which is equal to 1 squared. So that means that y1 is just equal to 1. And then we've been given our second x value, x2. x2 is equal to 1.1. So to get y2, it will be f of 1.1, which is equal to 1.1 squared. So we'll have that y2 is equal to 1.21, because 1.1 squared is 1.21. So from here, we can now substitute into our gradient formula. So we'll have m equals 1.21 minus 1 over our x2, which is 1.1 minus 1. When we put that into our calculator, we get that our gradient is 2.1. And we want to show that we know how to answer this. So we want to write, therefore, the average rate of change is 2.1. Okay? Does that make sense? Yes? Go to the next page for me. Okay, so that's all average rate of change. So average means gradient formula. When we find our instantaneous rate of change, so while the average rate of change is the average of these rates between 2 points on y equals fx, the instantaneous rate of change at 1 point y equals fx is the actual rate at that singular point. This is measured by the gradient of the tangent. So what we have is for any function f of x, we can find the instantaneous rate at a point by finding the gradient of the graph at that singular point. So the gradient of a curve shows the rate of change of y as x changes. A tangent to a curve is a straight line that just touches the curve at 1 point. So we can see that on this graph here. So our tangent just touches at 1 point, and we can draw lots of little tangents along our curve. What we need to notice is the curve increases. If the curve is increasing, it has a positive gradient. So when the curve is increasing, it has a positive gradient. Okay, so over here, we have that the curve is increasing between here Okay, so that part of our curve is increasing and it has a positive gradient. We have over here, this part of our curve is decreasing, so it has a negative gradient. And then what we have is we have that there is a turning point, which is down here. So where it goes from decreasing to increasing, that is called our turning point. And that means that the gradient is 0. What we can also do is a turning point is also called a stationary point. As well, but we'll look into stationary points a little bit more as we get into Year 12 work, but a little bit for this as well. So with our next example, on each curve we're going to write the sign of its gradient along the curve. So wherever we have a maximum point or a minimum point, so we have a maximum point here, that is where our gradient is 0. Now, from negative infinity to that point, is our gradient positive or negative? Are we going up from the left to the right? Are we increasing on our graph? So that means that we have a positive gradient all the way along here. Then, from our point where we have our turning point and our gradient is 0, our graph is decreasing. So because our graph is decreasing, that means we'll have a negative gradient. Okay. Do you think you can give B a go at putting plus and minuses and zeros along it? I'll give you 30 seconds to give that a go. Yep, the roll connected. The easiest thing is to find your zeros first. Okay, we should have that from the left to the right, it goes positive, then it goes negative, then positive again, and then negative again. Okay, so we could say that for B, our graph increases, decreases, increases, decreases. Does that make sense? Yep, great. So we can find the gradient of a curve by measuring the gradient of the tangent to the curve at different points around the curve, and we can sketch the graph of the gradient values, which we call y equals f dash x. Okay, this is our gradient function, so we can sketch our gradient function, which we also call our derivative function. So when we're differentiating a function, which we will do in this topic, we are finding the gradient function. So all of this ties back to gradient. Now, when we have our f dash x, it is read as f dash of x. Okay, I just say f dash x, skip the of. So to sketch the gradient derivative functions, if we have that our f dash x is greater than 0, that means that our gradient is positive. Sorry, I didn't leave much space there. So that means the gradient is positive, and that means that when we draw our derivative function or our gradient function, it is going to be above our x-axis. Now, if our f dash x is less than 0, so our gradient is less than 0, that means our gradient is negative, and that means the gradient function is below our x-axis. And then, if we have that f dash x equals 0, or f dash x just means our gradient equals 0, that means the gradient is 0. Okay, and it means the gradient function is on the x-axis. So, with our gradient function, because it comes from the original function, what we say is that we differentiate or derive the original function to find the derivative function or just the derivative. So this process that we're doing is called differentiation. we are going to go to the next page when you are ready. What we are going to do, and we did this activity last year for your taster lesson, is we're now going to sketch the gradient function for each curve. So what we have is, what we want to do on our original function is we want to put our pluses and minuses and our zeros where our gradient is. So at x1, x2, and x3, they are all zeros. Sorry, I realised I did that in red and not pink. Okay. And then from negative infinity to our x1 point, our gradient is negative. Then we have that it's positive between x1 and x2. Then we have that it's negative again. And then we have that it's positive again. So what this means, we have that it's negative there, negative there. We have our zeros at those points, and we have that it's positive. So what we want to draw on the graph below is we want to put where our x1 point is. So we want to go directly down and put where x1 is, directly down where x2 is, and directly down where x3 is. We want to label those points. Okay, so if our gradient is positive, that means we want our graph above the x-axis. Okay, so where between x1 and x2, our graph is positive. So between our gradient is positive. So between x1 and x2, our graph is going to be above our x-axis and then come back down. And then between x3 and infinity, our graph is going to be above our x-axis as well. What we then have is if our gradient is negative, it's below the x-axis. So what that means is from negative infinity to x1, it's below our x-axis. And between x2 and x3, it's below our x-axis. And then what we just have is if our gradient equals 0, it is on the x-axis. Okay, so at our x1, x2, and x3, the gradient was 0, so it's on the x-axis. Where it was negative, it was below the x-axis, and where it was positive, it is above the x-axis. Now, obviously, we want to just draw that as a nice smooth curve, so we don't need to do it in bits, but we can do it in bits. What you'll notice is that with A, we have 3 turning points, 3 stationary points. When we differentiate, our stationary points go down by 1. So what this top function is that is an even function because both endpoints are facing up, and it's called, that one there is a quartic function, so that's an example of x to the power of 4. This one down here is a cubic function, so y equals x cubed with other things going on, obviously. So what we have when we differentiate, our power drops by 1, okay? Now, looking at B, we want to do the same thing. If you want to go ahead and try and do it by yourself, you can. I'm going to start doing it very quickly though. What we want to do is where we have our turning points, we put our zeros. We put on our graph where it's positive, where it's negative, and where it's positive. Okay, we want to identify that, and where our gradient is positive, our gradient function is going to be above the x-axis. Where our gradient is negative, our gradient function is going to be below the x-axis, and where our gradient is 0, it's on the x-axis. We want to put where our x1 and our x2 are, and then we need to, our gradient starts positive, so we want to start above our x-axis, below our x-axis, and then back above our x-axis. And so what you will notice is that our original function that we started with was a cubic. Okay, so it pretty much, this then followed and went to a cubic, what we started with. Our derivative function is a quadratic, so a parabola. So what we have is that we went from x to the power of 3 down to x to the power of 2. If we were then to differentiate our parabola again, what do you think that would look like? A straight line, okay? How cool. So, like I said, we have our stationary points. This is the end of our thing. So, our stationary points on our curve are where the gradient f dash x equals 0 are called our stationary points. That is what we have highlighted in the yellow up above. So, our stationary points were there and there on that function. And that's because the gradient there is neither increasing or decreasing. The curve the curve next to it, shows we have a minimum turning point and we have a maximum turning point. So a minimum turning point is the gradient of the tangent changes from negative to 0 to positive. Okay, it's when it's concave up, like if we just to look at the parabola. And our maximum turning point is where the gradient changes from positive to 0 to negative. And we have another type of stationary point called a horizontal point of inflection. So we have our maximum, our minimum, and our horizontal points of inflection, but we will look at those in more detail later.